just want to keep going. You write down this. All right, we'll write down some guesses up on the board here. Anyone who wants to. But if you have a guess privately, you can write it down too. But so people already have them ready, right? What'd you say? 7 point what? 7.35. 7.75. 7 point what? 7 point. Anyone else?
7.75.
7. Oh, that's up there too. Anyone have a different thing that's up there? 6 point. Oh, 8.2. Okay. You might be right, you guys. I don't know. What did you have something different? 7.687. Anyone else want to throw up a guess here? Okay. That's cool. I just wanted to hear, at least from the crowd, what kind of answers we're getting. Okay. Again, if you have your answer written down privately, we can compare it to a minute here. So hopefully we'll get the arc length, but first we need to build up a little bit of theory here. So what does it mean to find the arc length of a curve? Well, as we've said, it's almost very close to every day of this class. Let's pretend that it's not a curve. Let's pretend that instead it's a bunch of line segments, right? So this is a picture. This is not the curve we're currently working on. We're just kind of developing a general idea of how to maybe get in on this problem. So you take some smooth curve in red and partition it into a whole bunch of pieces. And on each piece, we just declare it to be a line segment, okay? And that's not going to be a bad estimate. In fact, it's akin to maybe even what you were just doing now. I mean, you're just, you kind of approximated it in a similar way. And now for each one of these segments, say this one right here, how would you calculate the length of that segment right there? The distance formula, or what else is equivalent to the distance formula? We also call it what? Slope. Yeah, the Pythagorean Theorem, right, is also the other name for the distance formula, right? So in typical calculus fashion, if I call this side delta x and this side delta y, then this side is equal to yes, very good. It's by the Pythagorean Theorem. That gives us, for that one particular segment, if we're zoomed in on one particular segment, that gives us, for that particular segment, whatever the delta x is, whatever the delta y is, it gives us, by the Pythagorean Theorem, this, just for that piece. Well, of course, if we have a lot of them, it makes sense then to add them all up, right? So you do that for every single delta x, delta y along the curve, and you'll get your approximation. And then, of course, like we've done many times so far in this class, we'll let whatever expression we have, we'll let n, the number of segments that we have, go to infinity, which also implies that delta x goes to 0. So this is not a very satisfying formula yet, but it certainly captures what we're trying to do. But the only thing left to do, maybe, is to do some algebra and try and come around this with like some more formal language with integrals and all that kind of stuff. Give everyone a second to digest what's there. I'll show you how to get this into an integral. You're beginning to see, even in this unit, that integrals are not just that area under a curve, but they're used for summing up any infinite thing. It could be the sum of underneath a probability function. It could represent a probability. It could be the integral of a density function if you're in physics class. And what do you get? The mass, right? It could be, an integral is just a tool for summing stuff up. So in this case, recently we've been summing up cross-sectional slices of objects. Or now here we're going to be adding up a whole bunch of lengths. Okay, well fine, whatever we're doing, we're adding up an infinite number of things. So let's do just a little bit of algebra to convince ourselves that we can write this as a nice integral in a form we like. This expression, this is a little bit of a trick here. Come on, you like that? I have not changed the expression, do you agree? I'm dividing by delta x and also multiplying by it. So that's a little tricky. But now inside here, do you agree that this is outside the radical, this one. But I can bring this one inside the radical by squaring it and then bringing it in. Yes? Still, just want to recognize that at every moment along the way here, we still have the square root of delta x squared plus delta y squared. Do you agree? All the way down to here. And now let's just recall that the thing we're trying to do is take this as n goes to infinity and delta x goes to 0. We're trying to sum this up. And when we do that, what happens to delta y and delta x? Well, they go to 0. And we call this quantity, what name will we now give it in the nomenclature of our class? dy dx. dy divided by dx, my friends, is an object of great interest to the calculus students. That's the derivative of our function y with respect to x, dy dx. And this will be dx, and we'll sum them up using an integral over the interval of interest. So here's the arc length formula. It's just this, with d's instead of deltas, and on the appropriate integral. So let's now do our sine x finally. Here we go. This is the big moment. Of course, I don't think I have to tell you, but this dy dx in here will be, for us, cosine x. And now, I will just say that I think they've manufactured one or two problems in the homework that you can do by hand, but generally, this formula produces integrals of a form that are very, very hard to integrate by hand. So often we will reach for a calculator on these. They have, like I said, they have some on the homework that they've designed very, very specially so that you can do them by hand. So do that. But in general, you just pick sine x, the square root of 1 plus cosine squared. Not something you know the integral of. Really nice to get here. And there it is. Feel free to fn this. From 0 to 2 pi is what we're doing. So who wins, friends? Yeah, the 7.625, I think, is the team that wins here. Wait, is this? Yeah, that's the closest, I think. Unless someone else said something different that was even closer, I don't know. But now I don't know. Should I give? How about I give? Okay, the prize is you get additional stickers. Because I think there are a bunch of you. Maybe there aren't. I don't know. Okay, so raise your hand if you got 7.65. So you didn't volunteer your answer. I got 7.69. You gotta be more bold about it. Here, it's exciting. What are you gonna do with your extra stickers? Yeah, don't spend them all in one place. Anyone else good? Very close answer like that. Anybody else just wants some more stickers? Yeah. There you go. Anybody else need to buy more stickers just for fun? There you go. All right, questions or comments? Let's stop here just for a second. Questions or comments on this process, the theory, the answer, the calculator, anything? You like this? This is the kind of thing that you'll maybe, I don't know, it's not so hard that you couldn't rederive it quickly, but you may, after doing the homework tonight, you may have committed this to memory at some point, right? Square root of 1 plus the derivative squared. Integrate.
Is the homework being checked tomorrow or is it being checked on Monday?
I think we'll check on Monday. Okay, it'll work for you? Does that work for you?
I'll just clarify.
Okay, as long as it works for your schedule. All right, so let's try a little, divergences from this. I'm going to give you two functions that present to us a little bit of a challenge. There's not much more to say on the kind of problem we just did if you just apply that formula. So let me give you two problems, if I can do it here before the end of the period, that present a little bit of an issue for us. You didn't notice this on the previous slide. One of the demands is that this be differentiable. Why is that a demand? Because what appears in the formula? Yeah, I mean the derivative appears in the formula. So if the function is not differentiable at some point in the interior of the interval, then that's a problem, right? So I think it goes without saying, maybe even though you haven't looked at this curve, that this is not differentiable at what particular place? At x equals 0. Yeah, we have a different slope from the left and from the right on this curve as we approach 0. So this is going to be a little bit of a problem, but not too much. It's still a continuous curve. It's still defined for all values between -4 and 4. So here's what we'll do. We understand that, we could, just take the absolute value function. Can we find the length of the absolute value function on some interval, even if it crosses 0? Like, yeah. We just need to break it up into two pieces. So that's the first issue and the first solution to that issue that we'll encounter is what happens if we encounter something that isn't differentiable like this. And we'll do what I just said. We're going to break this up into two pieces. So let me first rewrite y just to convince you that y is actually maybe better defined this way. If x is positive, what function are we really talking about here? If x is positive, then what's the absolute value of x? It's really just x. So what function is this? If x is positive, it's x squared minus 4x minus x, which is minus 5x. And if x is negative, then the absolute value of x is really what? Negative x? Yeah, that's really what this is. So we get x squared plus 4x minus x, which is x squared plus 3x. Huh? So we need to do it a little more slowly. So here, for this first one,
I get the first part, the second part.
Okay.
With the absolute value.
We'll leave this empty thought up here. All right. This is x squared minus 4 times negative x minus x. So the absolute value of x when x is, this is not the graph of our function, this is the graph of the absolute value of x. The absolute value of x is equal to x when x is positive and negative x when x is negative. You could put or equal to either of those, right? Yeah, how do you compute the absolute value of negative 10? The answer is you do negative 10, right? So, good. So now we have this, and really the rest is, I think we've navigated part of the issue here, right? So we just add this up. Go from -4 to 0, apply your formula, plus 0 to 4, apply your formula. So let's pull this from the previous slide. It's the square root of 1 plus, now on this interval, we're talking about this function here, right? So let's keep this stuff straight. And on this interval over here, we're talking about this function. So what is the derivative? For negative values, the derivative of this will be 2x plus 3 squared dx plus square root of 1 plus something else squared dx. Well, here it's 2x minus 5. Okay, and then as before, call this L the arc length. We'll just FNN those, right? So we'll wait for someone to come up with an answer there. But feel free to stare at this for a little longer here. You comfortable with the work we've done? This idea of how to split this up to avoid this differentiability issue? Yeah, I mean the units will be whatever the units in x and y are, right? If you have inches, is what we've just been doing, so the inch will be in inches. But I don't know that they'll come up. I mean, if they're, I don't think it'll come up. But if it were to come up, I mean, you could say these are in meters, then your answer would be in meters or something, you know. That'd be fine. You don't have it yet? Good. This is the total, 19.556. Did anyone else run it? Did you get it? Same thing? Good. Math is working. Okay, one more issue. We can hit it before we close out today. Finding the length of this. What's the issue here again? This actually seems pretty tame. Just the cube root function. But there is an issue. What is it? Yeah, it's still not differentiable there. And the issue on this one is that even if we run right up to that boundary, it's still not differentiable there, right? And so that's a problem. There's not even a left or right-hand derivative at that point. It's infinity, or from both sides. So I'll draw the picture. Oops. I'll draw the picture, but I'm going to redraw it too. So the picture of interest is, of course, this curve, right? And we're doing this on the interval -8 to +8. This is the curve, the length of which we want to calculate. You can try breaking it up again like we did before, but I promise it won't work. You'll still have, when you go to put that derivative in, you'll have an expression that is undefined at the endpoints of your derivative. So that's a problem. But of course, we just need to stop and recognize that this is the same problem as finding the arc length of this curve, right? Y equals the cube root of x cubed on -2 to 2, right? A reflection over the line y equals x, guys. A reflection, it's the rigid motion, right? It preserves distances, doesn't it? So if we've done a rigid motion here of some kind, a rotation, or in this case a reflection of some kind, or translation, then we still have this. Look, if we can answer this question, which is quite easy, this is differentiable the whole time. Then that will be the answer to our question too, because it's the same length as the picture we have. So I mean, that's the real story. So we'll integrate instead the function -2 to 2, this function, y equals x cubed. So 2 ways to handle this differentiability issue. So we'll run that through. Come up with an answer. My slope on this second one doesn't look like 0 very much there. Yeah, final answer there was what? 17.265? 165, someone confirm?
No,
261.
Yeah.
I don't know why I heard 5. 17.261. Other people? Thank you. Okay.